what I thought we'd do is maybe just say 5 minutes about your project, what's uppermost in your mind, and then we'll have a little bit of a discussion with. So, off you go. Are you all mic'd up? Yeah, everybody's mic'd up. Okay. Thank you all. Hey, congratulations. I think wonderful. Please, Chuchu.
Hey, really feel honored to get this prize. Actually, I'm an Illinois alumni, as Shankar pointed out. My last year of PhD was also sponsored by another Tom's company, the Energy Institute, Civil Energy Institute. This is my second year as an assistant professor at MIT. Really feel happy to be able to join this Tom's sort of cohort again. Our project, as just shown on the web page, on the screen, is about compositional neuron certificates to protect the safety-critical infrastructure. So our idea is to bring up data-driven AI machine learning technology together with some of my background in control theory and formal methods that use some sort of rigorous mathematical analysis to do failure identification, isolation, and recovery of systems. Now, what we see in the strengths of bringing these two methods together is actually bidirectional. These traditional rigorous methods, like in control theory and formal methods, they are really rigorous and they want to prove guarantees. They want to give you a mathematical proof of all the properties that we want to have. But they suffer from the complexity issue. They suffer from scalability. All these, we know these, like what we call certificates. By the way, when I say certificates, it means a special kind of mathematical proof we want to give to the system. Those certificates, we know how they should look like. We know how the rules of those certificates should satisfy, like the Lyapunov condition. But it's really difficult to really express those certificates in a nice mathematical form, because if we use the traditional control methods using a linear function or nonlinear function to express it, it's just difficult to figure out the right expression. Now, using the power of machine learning, especially the expressiveness and all these nice tools in the machine learning community, we can bring those methods alive again. Now we can use a neural network to express those certificates. So that's this direction. On the other direction, we can start to think about what kind of failures and attacks that could happen in AI-based infrastructure system, and sort of use those formal methods and control theory to bring a nice safety bubble or safety shield on top of the critical infrastructure. And what we propose here is we can actually learn those safety bubble for each node of the network. Now we have the flexibility to compose a global certificate using the local ones, using the local certificates to give us system-level guarantee. But we have the flexibility to compose them in a way that we like, and we also use these certificates to develop some monitors that can help us identify the input signals, whether they are normal input signal or they could be attack that could bring the system away from the status that we want it to be, like some stable state. And if that happens, do we have the capability of bringing the system back to the normal state? If not, we can raise an alarm, at least to some human operator, and isolate this attack, let the human operator fix this issue. So that's the sort of the overall idea. This is really a seam integration of the rigorous methods and the data-driven approach. So that's pretty much what our project is about, and I feel like this is a unique opportunity to bring the safety and provably correct infrastructure to the next level.
Let me just say, she's using the methods of Lyapunov, Alexander Mikhailovich Lyapunov, and when I see the University of Kharkiv being destroyed, I mean, it is the home of this wonderful science and this wonderful tradition. Of course, St. Petersburg was very, very important, but, Kharkiv was no slouch. And so anyhow, I just think we should think fondly of Kharkiv as when we think about Lyapunov. So please.
So insider threats are a grave problem for many enterprises, and it's a very difficult problem to deal with because the insiders have a lot of knowledge about the organization that they can make use of in carrying out their goals. So an obvious way to deal with it is least privilege, where you don't give people any more privileges than they need to do their job. But it's really very hard to do that. Most organizations probably don't have very good understanding of exactly what responsibilities the parties they have beyond a certain level, and no formal model of that could be checked for broad parts of the organization. A good example is hospital systems and electronic health records. The doctors have to be able to get access to the health records in emergencies. And so the consequence is that you have relatively little least privilege. You have organizations of large numbers of employees and large amounts of data where a lot of access is given. So a strategy that is commonly deployed on this is to try to do some sort of machine learning to try to determine, to re-engineer your processes of your organization from looking at the logs of the behavior. And so if you can do that well enough, then you might be able to at least mitigate the damage of the insider threat by quicker catching of the parties. This sort of work, though, hasn't been much explored from an adversarial perspective. And so the question is, if you're an insider and you go after a record because it's a VIP that you're interested in or something in the hospital case, then how are you going to alter your behavior to make yourself difficult to detect? And an insider is likely to know a lot about what would be the limits of the detection algorithm that's being run and of these things. And so the idea on the proposal is to look at some of these issues. We need to look at questions of how one does the learning in what phases. So you have a continuous stream of incoming data, and you need to refresh your knowledge of the enterprise at some interval. And it's not clear how one does that because in different domains it has different impacts. And then explicitly, there is a question of what's the best strategy for the adversary. And we found some fairly surprising things from preliminary experiments with this, that the attacks don't necessarily come out the same way in different contexts. So what works in a networking context might not work in an enterprise context. And then finally, all of these things are efforts to winnow down problematic things to a level that they can be reviewed by humans, because they can't pursue an insider threat based on a purely automated case in many instances, especially like the hospital example. That's not really feasible. And there's going to be a lot of false accusations as well. And so one needs to find a method to do this so that the operators are not overwhelmed. And often you can do this with at least help with some domain-specific knowledge that goes above the level of that's integrated with the AI. An example might be like if someone accesses a patient's record once, and that was considered okay, then if they access it a second time, that would be considered okay as well. The machine can't infer that. It's got to be somehow input to the system by people who understand what the system's goals are. Okay.
Hey, can you say something about your other project also on the transportation, in non-Italian job, but I know you're part of it.
Yes, we have another one. This is the I-24 mobility. So the idea is, this is a Berkeley team, has a set of algorithms for autonomous vehicles, and they're looking to do a major study of them with actual in-the-field vehicles going on the I-24 highway. Now, we can't get them to do adversarial things, okay? But the thinking is that maybe there's a way of learning something that would be helpful for adversarial detection, like attacks on traffic flows, by at least asking things like, could you learn and detect the algorithm that's being used for the automation? And so could we pick out of the I-24 traffic the ones that are operating under the certain automation algorithm? And so that's the other.
Thank you, Carl.
Over the last, it's been 20 years, we've been
looking
at...
20 years. Sorry, I said 10.
We've been looking at how we can use machine learning in systems that are making sensitive decisions, so security-sensitive decisions. And what we quickly realized is what Mr. Kasparov pointed out, which is that it's incredibly important to have a human in the loop. That even the best algorithm that we can come up with is going to have blind spots. And so we're faced with this challenge of, so I'll give you the example of malware, right? A typical malware antivirus provider will receive anywhere from 10 to 40 million samples per day. And some of those samples, the vast majority of those samples are going to be benign, but some of those samples will be malicious. There'll be things that are well known, there'll be techniques that have been seen before, and the algorithms can easily, the machine learning algorithms can easily pick out those as malicious. Yet every day we read about these persistent attacks, SolarWinds, Equation Group, and other things. When we go back and look at the providers, we find that they've seen those samples. In fact, they saw those samples right when the attacks were launched because they were flagged as being kind of weird or something and sent to the antivirus providers. But they weren't actually marked as malicious because there simply aren't enough computational resources to be able to, say, spin up a virtual machine and analyze every single one of those resources, samples that comes in. But what if, on the other hand, the machine learning algorithms could flag a limited number of those samples that come in as, well, this is really questionable. I don't know whether or not this is something malicious or not, and so I'm going to ask the human expert. As soon as you show it to the human expert, they're like, this is malicious, right? The challenge is designing the algorithms that can detect those things and then have a budget for working with a human, because I can't give the human all 40 million to look at each day. So that's what we work a lot on, is those kinds of algorithms with human in the loop. Now, in the context of this grant, we're really excited because the challenge is going from the theory and designing these algorithms to how do you actually deploy them. So it was roughly about 15 years ago at the early stages of cloud computing that we argued in favor of using the cloud, that the cloud offered benefits around cost, around efficiency, around staffing, and around cybersecurity in terms of centralizing resources. Also networking and OpEx instead of capital expenses and so on. That was a very seminal, impactful paper. It has really defined how people use cloud computing in the Fortune 500 and beyond. But there still are people who won't use the cloud. And I thought it was interesting because last night I was sitting with a bunch of C3 folks, and they said, you know, yeah, we have some customers who they run C3 not in the cloud, but in private deployments in their data centers. Why? Because they have super sensitive data. They have super sensitive algorithms, right? Developing a machine learning algorithm, tuning a machine learning algorithm, and setting its parameters could require data sets, constructing data sets that cost millions to tens of millions of dollars. I don't know that I want to put that out in the cloud, right? If I don't trust that the cloud security is sufficient. You'll never find Coca-Cola running financial modeling in a public cloud because of the risk that they might be on the same physical machine as Pepsi doing their financial modeling. And if there's a bug in the software, there could be a leakage of information. No CFO wants to be the person who has to tell the CEO that their data just leaked, right? But today, we have technologies that can allow us to remove that software component from having to worry about the security of the cloud. There are trusted execution environment technologies based on hardware in the chips. Intel calls it Secure Guard Extensions, or SGX. ARM calls it Trust Zone, and so on, that allow us to now have our trusted computing element be the processor itself, storing our data, storing our algorithms encrypted, and only decrypting them inside the processor. And so now we can take these algorithms for adversarial machine learning that we've developed and potentially be able to deploy them in clouds like Azure Confidential Computing and allow people to run C3 suite applications in the cloud, computing on their data always encrypted in rest, encrypted while it's being transported, but only decrypted inside the processor. And so that's, for us, it's really exciting. There's going to be lots of technical challenges that we're going to have to face in terms of working with the Azure environment. But we think it'll be really exciting to finally be able to take these algorithms we've developed and push them all the way into the cloud.
Fantastic. Bo.
Thank you for. So,
hey, you're like the global winner of the largest number of projects, so cover as many as you can.
Yeah, I will mainly talk about the privacy, robust, and expandable federated learning we deployed, proposed here. So our proposal is mainly driven by many real-world applications. And I will give one example, which is from Amazon, that they have, inside the Amazon, they have their team to do the fraud detection. And the fraud detection data come from different like teams from Amazon. Therefore, they actually want to train it jointly and leverage knowledge and information from different teams. But of course, as Anthony said, there is privacy, there is like moving data, computation, expensive, heavy load. So there are a lot of things you cannot do, and in real world, the limitations. Therefore, you only be able to do distributed learning and therefore satisfy certain constraints. And when we do distributed learning, there are many problems come up under the big umbrella of trustworthy machine learning. So privacy is one, as we mentioned, because different teams have sensitive data they don't want to share. And the robustness is one, because during training and test time, you can have a bad user contribute to noisy data or bad data, then the whole model may be hurt by one of the adversary agent. And during testing time, of course, there are different threats as well. And further or more, we can see, we also hope this distributed setting can be expandable to each user, like why on this joint model, your accuracy is this much, but the other agent actually have higher. We both contribute data, but why, right? Is that because my data is too noisy, or because you actually didn't give me enough resource for my data to train? So these are a bunch of like real-world challenges. Therefore, in our proposal here, we focus on mainly two paradigms of federated learning, like horizontal, which means each local user have part of the data, which is very realistic cases, and the vertical, which means each user have part of the features. Say they can be different features, or they can be different modalities, like some team have images, some team has text, videos, audio, like that. So this is quite realistic. So therefore, we want to jointly look at these two paradigms and see how to solve the three problems we mentioned, like privacy, robustness, and explanation. So in terms of privacy, what we do propose here is that in addition to the improvement of standard differential privacy framework derivation, we hope to do a more generic way for privacy-preserving generative model from the joint data. Therefore, you can generate the data, and the data can be further used by other downstream tasks for the local users, not only the joint like global model. And then the problem comes, like if the data is high dimensional, and if you do generative model, it's almost impossible to guarantee the privacy. So you have to compress the dimension of the data so that you can add noise and still guarantee DP, but you can achieve good utility. Then there is a balance, like how much you compress and how much data utility you want to preserve. So we here propose like gradient compression algorithm that we are able to prove the convergence of, after you compress the gradient and add the noise, what's the convergence of the whole training process, so that you can guarantee certain types of the utility. That's the privacy part, and this can be applied to two framework, like horizontal and the vertical we mentioned. And in terms of the robustness, we mainly focus on the training time threat, because in the distributed setting, the training time threat is very unique. And of course, the test time threat, we can actually use some existing or prior work tools to integrate to the platform. About the training time threat, there are a lot of like how you can identify different users as their data deviate from the main distribution, or they actually, even they deviate, there are two types. One is this is not useful data, like this noise, or they are actually very useful in the non-IID setting, so they actually bring good information to your whole joint training. Therefore, we need to identify these two cases, and we, of course, like the later one, which can contribute, but we want to remove or identify the former one, do not use their like noisy data or bad data. That means we will use one thing called Shapley value, which is created in game theory, and then it's got a Nobel Prize too as a like a game, so that you can contribute. You can compute the contribution of each like agent participant in the game. We also hear Gary talk about the game theory. I think game theory is indeed quite useful in our cybersecurity area to model the dynamics among different agents and defenders and attackers, etc. So our idea here is that we can contribute sharply for each agent data level, feature level, and like agent level, so that we can know whose contribution is less with a relatively small set of validation set, and then therefore we can identify the important one. And the challenge here is that the Shapley itself, computing is super complex. It's 2 to the power and like exponential complexity. So we need to reduce it to linear or approximately linear complexity so that we can calculate in the real deployment system. That's one main thing we work on this training time attack part. And in the explanation part, actually, we can first, a byproduct is that we can leverage Shapley to give the explanation quantitatively, not only look at the attention and things. So that's the first thing. And the second thing is we can provide some certification of the influence function or existing different metrics for explanations so that we can see whether they are aligned and therefore to improve, provide the quantitative explanation for different agents.
Fantastic. Hey, so I must say, ever since Gary gave this talk and said you got to pay attention to the clock, I think I got to look at this clock in a. But I hope she has a lot to say about Shapley value and the computation of the games and doing it in real time. And I have to say, I mean, just looking. So Gary, I have to say, what has changed is really this way of thinking about multiplayer games. And really human-machine multiplayer games. I'll address it to you because these are themes that arose in your talk, and I hope you see that our group of scientists, and they're really bringing that to life. So I know that we're over time, but I'd like to give you sort of one closing statement of perhaps what you've seen or it's sorry to put you on the spot, but
no, it's a bit surprising, yes. But I just, it was, it's always great pleasure and honor to hear references. But one of the questions that I got was about a proof that human element is crucial, and I had 4 witnesses on the stage.
Yeah.
So it's again, I know the limits of my ignorance. I know where I should stop, not to cross in the territory where my credibility is questionable. But now it's while I had general philosophy and some of the pieces of evidence, now we just see that it's the front line of research. It's basically finding the way to make sure that the human role is crucial, and success depends very much on human participation. That's why I want to emphasize again, that's why we have an advantage here. And that's the real advantage we have to press. Yeah. So there's the free minds. And again, this is we understand. It's 20 years, yes? So how many failures? Many failures. But eventually, you succeed because you have this luxury. Yeah. So in Russia, you may not have the same luxury of working so many years and not providing results that your bosses wanted you to come up with instantly. So again, it's
Gary, thank you for a wonderful talk, and congratulations to all the winners. There's several more in the audience. I know that, so I should say, some people like Alberto and have won an award in every one of our 3. I think there are others. Somaye and Javad Levey are here as well. So great pleasure to have you all, and thank you, and congratulations again.